Perfect. So today we have Amihay Hanany tell us about simple modular spaces. Take it away.
Thank you very much. If you don't hear me, please let me know. Let me start by just giving an explanation for this talk. So we had a sudden cancellation, and I decided that we will have continuation to the series. But I'm going to take an advantage of this and revert to simple things, which are directed mostly to students. So if you're a student, please don't hesitate to ask questions. We will cover basic things, but maybe some of them are not that basics once you think about them. But we will see how those basic things match nicely with the notion of Coulomb branches. So I'm going to start this talk by asking what is a simple moduli space? What kind of criteria can we have to determine whether a moduli space is simple or not simple? So let's see what we can do. Right? And the first constraint that we will put is to restrict ourselves to symplectic singularities, or in the physics language, to theories with the 8 supercharges. The moduli spaces will show up there. Of course, there are many other moduli spaces in physical systems, but this is a restriction that we will give ourselves today and see what we can come up with. So the traditional criteria for simplicity are, the first one is freely generated moduli space. Actually, a lot of the part of the talk will focus on this part, because you could see that you could start with a very non-trivial theory, but as we flow to the infrared, the theory becomes just a theory of free fields. And when it comes to the question of the moduli space, it's just going to be a freely generated moduli space. The other criterion you can think of is to have a hypersurface singularity. So a collection of complex numbers which satisfy one relation. This seems like a simple description. In physics, it is quite common to use such a singularity, because you could always impose the single relation as a constraint using some Lagrange multiplier in a supersymmetric theory, or even if the theory is not supersymmetric. This has a natural generalization. Instead of a single relation, it will have a complete intersection, so number of relations can be higher than one. And again, this sounds like a relatively simple moduli space. And I'm actually going to challenge those 2 points in the talk over here to check whether it's really correct that those are simple moduli spaces. Now, a main tool for studying those questions is to explicitly compute Hilbert series for those moduli spaces. And I will show some of the formulas that one can do when computing such functions. Any questions so far? Okay, so let's first talk about the first case, freely generated moduli space. This is a copy of the quaternionic space to the power d. Do you see my mouse?
Yep.
Thank you. And in fact, there is a nice family of moduli spaces which are given by a Dynkin diagram. So if I take a Dynkin diagram to be a finite type, and the labels of the nodes be the Dinkin labels. Then all of those quivers have a Coulomb branch, which is a freely generated moduli space. I don't know if this is a known fact, but that's, well, it's known to us for several years now, but might not be known to other people today. There is another general formula I can write, that the dimension of this freely generated moduli space is the dual Coxeter number -2. Okay, so the generators of this freely generated moduli space are transforming in the spin 1/2 for a representation of SC2R. And and here I'd like to correct some misconception that I heard by several people, which say that you know, when we talk about free fields, so free field only has this property. It has spin 1/2 under SC2R. Any other R charge different than 1/2 is not a free field. So you know, call it something else. Free field is a reserved word. It's a field where the scaling dimension is 1/2. The R charge is spin 1/2 of SC2R, and that's it. Now, here's a non-trivial thing. If I'm taking a Dinkin diagram of finite type, and I compute the Coulomb branch, then there is a symmetry that I can read off from the Dinkin diagram itself. This symmetry I call the balance symmetry group. So it just consists of the nodes which are balanced, and we will see all of them are balanced except for one. And but on the other hand, since the moduli space is just a copy of the quaternionic space of D times, then the natural symmetry group is SPD. And so now I have an embedding of the smaller symmetry group inside SPD. Let's show this in an example. And actually, before we show the examples, here's a list of all of those finite type Dinkin diagrams with the explicit numbers. I guess we don't see the top one.
I see the top one.
You see it? I see. It's me who doesn't see it. Okay. So yeah, so here's the B type, the C type, the Dinkin labels. And note that the adjoint node is the only node which is not balanced. All other nodes are balanced. So over here, this is the B type. This is the adjoint node. That's the only node which is not balanced, and it has an imbalance of -1. Similarly here, the adjoint node is over here, imbalance of -1. Here, the adjoint node, imbalance of -1, and so on. All of those guys have all nodes balanced, leaving a subgroup, which is a Dinkin diagram of a smaller algebra that is the balanced symmetry algebra. And then we have this embedding into a bigger space. So let's see a simple example. I picked as an example the F4 Dinkin diagram. So here's the F4 Dinkin diagram. So we have 4 nodes. This is the fundamental node. This is the adjoint node. All of those 3 nodes are balanced. And this node has imbalance of -1. Now the dimension of the Coulomb branch is just the sum of those numbers, -1. So we compute that the dimension is 7 quaternionic. Now the balanced nodes form the symmetry group of C3, SP3. So that's what we have over here. And that joint node is connected to the third representation here, which we denote by 001. Okay, so this representation over here. This representation of sp3 has dimension 14, which is twice this number 7 here. And so that tells me that there are monopole operators associated to this node that connect to this node over here. There are 14 of them, and all of them have, because of the imbalance, R charge of 1/2. And since this is twice the dimension of the moduli space, I conclude that the moduli space is H7. So without too many computations, I conclude that the Coulomb branch of this quiver is H7. A very important point is that this representation, the third rank antisymmetric of sp3, is pseudo-real, which is also the property of the fundamental representation of sp7. And that's a necessary condition for having such an embedding. So this is the embedding. sp7 is the bigger group, is the symmetry of the free space. sp3 is the symmetry I read from the quiver. And now I have a nice embedding, which says that the fundamental representation of sp7 goes to the third rank antisymmetric of sp3. Any questions about this computation? Okay. Now, before I go to the next line, let me just explain what we have over here. In general, this is a complicated gauge theory. I start with a gauge theory, and there is a non-simply laced edge here. But in general, if you want to avoid non-simply laced edges, you can do that. You can take the other Dinkin diagrams. We start with a complicated gauge theory, U1, U2, U3, U2 again. And at the UV, there are plenty of objects. There are the scalar fields in the vector multiply. There are invariants I can form, which are Casimir invariants. And this theory looks very complicated in the UV. But as I flow to the infrared, there are monopole operators which are generated, associated to this node. There are 14 of them. They get the exact scaling dimension of 1/2, and the moduli space at the infrared becomes free. All of those complicated operators that I find in the UV are now forming into composite representations of those basic 14 monopole operators that I have. Okay, so that's quite a magical feature of the gauge theory that we are using. And it's a generic phenomenon because it applies to any Dinkin diagram of finite. Any questions about this point? Okay, so now let's take the last equation over here. So on the left-hand side, I'm computing the representation content of the quaternionic space H7. So I take the fundamental representation denoted here by this label mu1. And since this is a simple space, any operator in this theory is in the symmetric product of the fundamental representation. So that's what we get at the left-hand side of this equation. So the left-hand side constitutes symmetric product of the fundamental representation at power t to the n. So at t to the n, I have the nth symmetric product of the fundamental. On the other hand, I could just look at this quiver, and I have three topological symmetries associated to each of these nodes over here. And I can use those topological symmetries to compute the representation content under this SP3 and sum up all of the contributions, and this is what I get. So the label 3 here denotes that those are representations of SP3. Here, the first term denotes the adjoint representation of SP3 at order T squared. So those are what we would expect from an SP3 symmetry. I get the representation here, which shows up in the second symmetric product of the adjoint representation at order T4. And there is another trivial representation at order T4. And most importantly, the third rank representation, which shows up at order T and at order TQ. So that's an exact result. And here's the point here, mu3, right? So the moduli space is generated by the 14 generators associated with this representation of SP3, and any other operator is just a composite operator of those monopole operators. Any questions about this formula? Okay, so now what's nice about this formula? I don't know if you've seen this formula before, but such formulas will show up many times in our computations. This formula constitutes infinitely many branching rules. Let me show. So I just expand in powers of t on the left and on the right. So if I take the first power of t, I'll get that the fundamental representation of SP7 goes to the third rank representation of SP3. If I expand in t squared, so that's the adjoint of SP7, and you see that the adjoint of SP7, there'll be two contributions, one by taking this adjoint of SP3, and another by taking the square of this expression over here. So I get those two contributions. And it just tells me that in addition to the adjoint of SP3, I'll have many more operators over here, which are in the this representation. So it's the 002 representation of SP3, and they conspire in such a way that they combine to the adjoint representation of SP7. Right, so I should think of those as quadratic objects in monopole operators that conspire with the adjoint representation, the usual representation we get from the Quiver, to form a bigger adjoint representation of SP7. I could continue, expand to powers t cubed, that's what I get. And here there's a nice branching rule of the third rank symmetric representation of SP7 into representations of SP3. And I have infinitely many such decompositions. In total, this nice identity gives me infinitely many branching rules from SP7 representations to SP3 representations. Any questions? So notice here that even though we are dealing with free modular space, I got something already. I got a nice identity from this computation. It's maybe it's not a big deal, and it's just a decomposition exercise, branching rules, in just ordinary branching rules in representation theory. But using the Coulomb branch, I was able to extract some such nice identity, and in one relation, I encode infinitely many such relations. There's another example that I want to go over, but now much faster. This is the case where I take the Dinkin diagram to be E8 finite type. And so again, I expect that the moduli space is freely generated. The dimension is 28. Here's the adjoint representation over here, the adjoint of E8. And that's the only node which is not balanced. It has an imbalance of -1. And if I take this node out, I'm left with those nodes. All of them are balanced, and they form the Dinkin diagram of E7. So the symmetry group is E7, and the adjoint is connected to this node, which for E7 is the fundamental representation of dimension 56, which is again pseudo-real. So I get an embedding of a pseudo-real representation to pseudo-real. The moduli space is half of that, H28, in the symmetry group SP28, and I get the embedding SP28 goes to E7 with the fundamental of SP8 going to the fundamental of E7. Okay, and again, I repeat the exercise of the computation. Here are all possible symmetric products of the fundamental of SP28. And on this side, I get the compositions into representations of E7. Actually, this is a result that we worked out yesterday with the Julius. We were not sure about this, how it looks like, but that's the exact result. And let me just clarify that mu1 here is the fundamental of E7, mu6 is the adjoint, and mu2 is the second rank symmetric associated with this. Okay, so now I'm showing this example because I don't know how to find similar cases to this. So just have it in mind. Maybe you could do something nice with this. Take those identities, take these relations and show something nice with it. But let me proceed. Before that, are there any questions? So this particular form that we have, and I'm going back to my Quiver here, leads to a generalization. There is a natural generalization. Because I had this C3 here, and I had this node which is imbalanced. And this is C3, so I can make it C4 and make all of the nodes of C4 balanced. So this gives me no choice. There must be 1, 2, 3, and 4. And the node here is connected to the last node with a changing balance. So here it's balanced. Then I generalize to C5, I get this. There's the node, and so on. I get a family parameterized by K. This is the case K equals to -1, K equals 0, and K1 and greater than. Now, how do I compute the function here, the high-speed generating function? And I see that all of those nodes take part. So on the left-hand side of the arrow, I have all of those nodes appearing in squares, mu1 squared, t squared, mu2 squared, t to the fourth. And so I'll generalize it in this way and in this way. And this is a universal term, so I keep it. And the last node, 3, 4, and 5. This is the last node, 3, 4, and 5. And it shows up with the increasing powers. This indicates the imbalance. So imbalance of -1 corresponds to t to the 1. Imbalance of 0, t squared. Imbalance of 1, t cubed. And so K here is the imbalance. And the label K is just the imbalance of the family. And here's the general formula for this family. Any questions? So we have a nice family. And what can I do with this family? Before proceeding, I could just declare a criterion for a simple modular space. In all of those modular spaces, the highest weight generating function is a polynomial. Is a PE of a polynomial. The argument inside the PE has finitely many terms. And so this I will now declare as a criterion for a simplicity of a modular space. And I will call it polynomial highest weight generating function. And so now I will add it to my list, freely generated hypersurface complete intersection. And now the next criterion will be polynomial highest weight generating function. So here's one of those simple modular spaces. And in this case, because this node is balanced, I get a symmetry enhancement because now so this linking diagram is no longer a bigger linking diagram of a finite dimensional the algebra, but we will see that we can extract a finite dimensional symmetry. So here's the expression for the representation content of the operators on the Coulomb branch. I find that there is no free part, so no linear powers of T. I also find that there are no odd powers in T. All powers in T are even. And this is actually an important point because another feature that I have is that all of those representations that we find over here are real. The symmetry group here is SP4. And SP4 has a collection of representations. Some of them are real, some of them are pseudo-real. But in this modular space, all representations are real, no pseudo-real representations, and no odd powers of NT. So we get a association between the property of being pseudo-real under the global symmetry and having powers in T. This is a feature which shows up in many more examples and just needs to be exploited with reference to other considerations, which I will not go over. Any questions? Okay, so the extra monopole operators that I find at way 2, due to the fact that this node is now balanced, gives me an enhancement, and I get an E6 modular space. And I find that this expression for the highest weight generating function gets an expansion like that, where mu here refers to the adjoint representation of E6. So here's the first expansion. Now this is an expansion in T squared, with left side and right side, which tells me that the adjoint of E6 decomposes under this embedding of SP4 to the adjoint of SP4 of dimension 36 and the fourth representation of SP4, the one here, of dimension 42. And again, I have this case where if I expand on the right-hand side, I get the nth adjoints of E6, and on that's on the left-hand side, and on the right-hand side, I get the composition into representations of SP4. Any questions? infinitely many branching groups. We now turn to the case k equals 1 in this family. Now we do have odd powers of t, and we also have, this is the only representation here, which is pseudo-real. All of the other guys are real. And so we get an association of odd powers of t with pseudo-real representations of SP5. There is no additional enhancement because there are no longer contributions at order t squared. The only contribution of t squared comes from the adjoint, and so no additional enhancement. And that's the behavior of all of the members of the family for grade k greater than 0. Okay, so we have this family. Let's look again at the family. This family for any k, where there are 3 cases to consider. K equals -1, where the moduli space is fully generated. K equals 0, where there is an enhancement of the symmetry, and the moduli space is a minimal nilpotent orbit of some algebra, in this case T6. But in all other cases, we can go over and check that I get minimal nilpotent orbit of some algebra. And the cases k greater than 0, this is the first one, we will have some non-trivial moduli spaces, but all of them have a polynomial PE. Polynomial highest weight generating function. Okay, I'm done with this, with going over this. Any questions about what we said so far? Okay, so let's talk about the phase diagram of those theories. So let's look at the class. So here's the phase diagram for this family. The case with the k equals -1 is just a free space, copy of h to some power. It's not even a singular space, so I don't expect to have any non-trivial phases. All points on this space are equivalent, and from the point of view of phases, it's a boring theory. There's one phase, all points are just the same. And it becomes more interesting when k equals to 0. Then we found that the moduli space is the minimal nilpotent orbit of E6. It has 2 phases, the origin and anything else. And it's denoted in this diagram by just taking the 2 points here with the generation, which is the minimal E6. Okay. Now, if I take k equals to 1, then the phase diagram will have 3 phases with the generations E6 followed by C5. And whenever I increase k by 1, I will add one more phase with a degeneration that raises the rank of C by 1 until I hit the last slice, which is C k plus 1. So n here is just k plus 1. So we find that this moduli space, which has a polynomial highest weight generating function, also has a linear Hasse diagram. So this is my next criterion for simplicity. A linear phase diagram. So let's add it to the rules, to the set of criteria for simplicity. Freely generated hypersurface, complete intersection, polynomial highest weight generating function, and linear phase diagram. Any questions about this point? Either all is clear or nothing is clear. And I suppose we can find examples of both.
Everything is clear.
Sorry?
I just said all is clear.
All is clear for Antoine. Who else is like Antoine?
I also agree with Antoine. All is clear.
All is clear. Okay. Okay, very good. So
Everyone else is the opposite, or?
okay, so here's another family. This family shows up in the study of 6-dimensional fixed points and 5-dimensional fixed points. It's a family we looked at quite a bit, and here what I did was to take a member. This is the k equals 2 member in the family. That's the highest rate generating function. Again, polynomial highest rate generating function. That's the flavor symmetry. And again, k is the imbalance of the node over here, which is the only node which is not balanced. All other nodes are balanced. Look that it has a very similar structure to what we saw up to now in the previous two examples for E7 and for the SP family. So in fact, there is a nice challenge here to find all such families which have polynomial highest rate generating function. We know many of them, but we don't know all of them. We don't know that we know all of them. There's no classification. So it would be a nice problem to try and study such a classification. I will say some words about the phase diagram. Again, it's a linear phase diagram, and just like before, it starts with a case where the k equals 0 is an 8 minimal orbit, and each time I go up with k, I add a d singularity, d10, d12. It's one of those cases that if I compute the Higgs punch, then it's also a simple moduli space based on the criteria I wrote down with this type of phase diagram, except that because the lower singularity has no symmetry at all, we don't expect the Higgs punches of those quivers to have any global symmetry. So from this point of view, it's a challenge to compute the Hilbert series for the Higgs punch of those things. I don't know if anyone has done this computation. Now, let me say a few words about where it shows up in 5 and 6 dimensions. So in 6 dimensions, it will be the UV point of an SP theory with appropriate number of labels such that it keeps this anomaly free. In 5 dimensions, it's another SP theory with one less flavor, and again taking the UV fixed point. In those cases, I get this quiver as the magnetic quiver for the Higgs punch of the theory. Any questions? Okay, so I'm done with the case of freely generated, and I'm also done with having those families. So remember that with the families we have those which have a polynomial highest rate generating function, and those which have a linear Hasse diagram. Let's talk about hypersurface symplectic singularities. It turns out that the combination of hypersurface and symplectic are very uncommon. Right? I could demand a space to be hypersurface. There's plenty of those. There are plenty of symplectic singularities, but both is really restrictive. And there is a potential claim for classification of those. And I'll show you all of those that we know. And again, I'll give you a challenge. Can you find another one which I don't show? This would be very nice if there is a thing like that, or if one can show that there is a classification of all of those symplectic singularities, which are also hypersurfaces. So we know the dimension 1 guys. So I took here the ADE Dinkin diagrams, and if you compute the Higgs punch of those ADE Dinkin diagrams, they are all given by Klein Duval singularities, dimension 1, quaternionic. All of them are hypersurface singularities. And those are the only hypersurface singularities in dimension 1. In dimension 2, quaternionic, well, actually, this is just an elaboration. Let me say one more thing about the dimension 1 case. There are 2 leaves. So here are the Klein singularities. The dimension is 1, 2 leaves, there is the origin and anything else. And that's definitely a criterion for simple moduli space. So those will be included in the set of simple moduli spaces. D and E have no symmetries, and therefore there's no notion of a high-square generating function. For the case of A, n greater than 1, the symmetry group is U1. So again, I don't have any simple notion of a high-square generating function. For the case of n equals 1, I do have the symmetry group to be SU2, and there I know that the moduli space is the minimal nilpotent orbit of SL2, and therefore there is a nice high-square generating function. So all of them satisfy the criteria we said for simple moduli spaces. So here's the dimension 2 cases. Those turn out to be labeled by, it's a family labeled by n. So here there are several representations I can have. So you can take this quiver, 1 and 2, with n adjoint loops for the 2, and compute the Coulomb branch. The Coulomb branch is always 2 quaternionic dimensional. And I can also compute the representation content. The flavor symmetry is SU2. And so mu here is the Gaussian with respect to SU2. And I get all of those contributions over here. A polynomial high-square generating function. Hasse diagram contains of 3 leaves on a line, so they satisfy the criteria for simplicity of moduli spaces. So yeah, I would count them as simple moduli spaces.
So Ami,
yeah,
there is in many of these simple moduli spaces, the P, well, the HWG is not only a P of a polynomial, but the polynomial is always has this very similar form. In particular, there is often a weight times T to some power plus T to some power 2 more. And so is there an explanation for this pattern, which is?
I don't know the explanation, but again, yeah, there are always those 3 terms.
Yeah, it's very striking that.
There's the T to the 4th, which shows up, and I never found a good explanation y they stay to the fourth here. Then there is the same representation, which shows up with 2 powers that differ by 2.
Yeah.
And sometimes there is a negative term, sometimes not.
Yeah.
So negative term will be slightly more complicated, but not by much. So in the examples we saw, I only showed those cases where there are only positive terms. And so indeed, you're right. We need to find some explanations for that. Actually, you are reminding me, I gave a talk in the Weizmann Institute and offer so those 2 terms, 1 plus 2. And then he said, are you sure that there's no mistake over here? Because he's not used to this particular universal form of power. And I said, yes, I'm sure that it shows up in so many cases that by now it's quite a normal thing. So yes, indeed, this is a very good question, and we should wait for an explanation. You know, in terms of the, let's go back to the series. Let's take this series, for example. Here, what you get are the terms that show up in symmetric products of the adjoint. So mu2 is the adjoint. mu4 shows up in the second symmetric product of the adjoint. mu4 is in the third, sorry, mu4 is in the second symmetric product, mu6 in the third symmetric product, and so on. So those are representations from the nth symmetric product or the ith symmetric product of the adjoint. So all of those terms are accounted for over here. And if you find the formula, you'll see that all of them satisfy this criterion here. This is the universal term.
Yeah.
This is a generator of the moduli space, so it must show up over there. So it seems like the only guy which is lacking an explanation is the one over here.
Yeah. Okay. Yes. Thank you.
Any questions from the audience? Okay, so we were here, and so this is the moduli space which satisfies all of the criteria of being simple, including the point that it's hypersurface. But now let me show you a case where the things don't go so well. Here's the only known hypersurface singularity of quaternion dimension 3. It's the Coulomb branch of this quiver. Sorry, the Higgs branch of this quiver. Because there is a loop here, there is a flavor symmetry, which is SU2. And so the representations here are representations of SU2. And the moduli space is a complete intersection. So it is part of the criteria that we used at the beginning. It's not just a complete intersection, it's also a hypersurface. 2 generators subject to 1 relation. Actually, it's quite a challenge if you want to entertain yourself to write the relation of order 12 in terms of the 4 variables here and 3 variables here. This will be a nice exercise. It's not a simple expression. If I try to expand this Hilbert series in terms of highest weight generating function of SU2, then I will find that it's not a polynomial highest weight generating function, so it does not satisfy the second criterion. So that's an alarm. It's not such a simple moduli space. Another property of this moduli space, I don't have the figure over here, but if you draw the phase diagram, it does show on a line. However, the lowest slice is non-normal. And that's certainly not a criterion for a simple moduli space. So I would go now to the list of criteria and argue that hypersurface singularity, because of a single example, makes the moduli space not that simple. Whereas for the other cases, okay, so complete intersection is a generalization of hypersurface, so I should also question this point. But the other terms, polynomial high-square generating function and linear phase diagrams, are still very nice criteria for simplicity of the moduli space. Any questions? Okay, now I will. We are out of time now. It's almost 4 o'clock now, so I will just make final comments. Here I gave. This is an example of Hasse diagram, phase diagram of slices in the affine Grassmannian of G2. It's one of the nicer diagrams that we were able to generate using our studies. It follows the co-weight lattice of G2. So the Hasse diagram is a very simple object. All of the points are associated with the co-weights of G2. And the slices between those phases are explicitly written down. They are also of simple type. Most of them are of type A. Only towards the bottom, they become some unusual slices. Those 3 guys, right? So, except for 3, all of the slices, minimal slices, are of type A. The quivers are depicted in each node is associated with the quiver. So that's corresponding to the slice between the phase to the bottom. Now, here's a situation where the Hasse diagram is certainly not linear. It's 2-dimensional because the algebra of G2 is 2-dimensional. It's a simple Hasse diagram because all nodes are already known. They are just nodes on a co-weight lattice of G2. This is already a known object. So the Hasse diagram, the phase diagram is simple, but definitely don't expect a polynomial high-square generating function. It's going to be quite complicated moduli spaces. And the more points, more phases you'll have, you'll get more complicated structure. So no expectation here. You may argue that starting from this point over here, yeah, here. From the point here, the Hasse diagram is linear. That's the only place where there is a bifurcation. Everything else below is linear. And so you could say, okay, that's a linear Hasse diagram, but does it have a polynomial high-square generating function? And the answer is no. Try to compute, take this quiver and compute there is a symmetry group at G2, yes, but try to compute the high-square generating function. That's a highly non-trivial computation to make. So just the criterion for linearity is not sufficient, even though the Hasse diagram is simple. It's a simple known object. Yeah, so that's an example for moduli spaces which are not so simple, but the phase diagram is linear. So I need to include all of these criteria in order to get a simple moduli space. And now I will, I don't have time, so I'll just go to the, I'll just summarize. Let's go to the end. I'll do a few more cases. Let's just put the summary. So we went over criteria for simplicity of moduli spaces, and we found two of them: phase diagrams, which are linear and polynomial high-square generating function. And here's my list of criteria for simplicity of moduli spaces: freely generated, polynomial high-square generating function, and linear phase diagram. Thank you.
All right, let's thank Ami. Any questions?
I can ask one if that's okay.
Yes.
Yeah, so this was nice. Can you go back to the G2 Hasse diagram you presented near the end? Quite far away from the end, it seems.
Yes, yes.
Can you explain what the AG2 and the CG2 lines are corresponding to? Like, what kind of singularity are those?
Yeah, so we have an explicit quiver for them, and if you just take the difference between this quiver and this quiver, you get the quiver for AG2. That's a general feature. If you want to compute, if you take an arbitrary point and you want to compute the slice to another arbitrary point, you just take the two quivers and just subtract the ranks. You should subtract the ranks, and the flavor symmetry should be the flavor symmetry at the top. And so that gives you the quiver for the slice. So we know the quiver for this, so we can compute it. And so let me first explain why this shows up. Actually, these three guys go back to a work of a mathematician from Ann Arbor. His name is Bergkamp, if I remember correctly. Maybe Antoine Julius remembers the name.
Yeah,
I don't remember, but yeah.
Yeah, so he Bergkamp. Well, okay, let's try to figure this out. Now, what's special about this thing here? So you see, if you go up, to the point here. Here, these lines. This line is negative simple root of G2, or simple co-root of G2. This is another negative simple co-root of G2, and here is the other one. So we have one long wedge. Now, as you go down, the wedge here becomes narrow and narrow, and over here I can still fit a negative co-root, but here I won't be able to fit it. I'll go out of the Weil chamber, the principal Weil chamber, and so I have no choice. I must go to the next point, which is over here, and this creates this slice, which, if it was up here, it wouldn't be normal. Sorry, it wouldn't be minimal. So I can go from here to here. It will be this slice and this slice. And it will be just this guy over here. But it's not minimal. Over here, it must be minimal. So that's this AG2 guy. And there is another which happens over here because I don't have this negative simple co-root. I can only go in this direction. So 1, 2, and 3 are those cases that, because of the narrow feature of the Weil chamber, I must have those special singularities. So we find that the thing which is special about minimal G2 is that it just doesn't fit. I can only fit this one into the minimal slice. This is a feature which happens for symplectic algebras as well. Each time you go to the origin of the principal file chamber, it becomes too narrow over there, and therefore you'll find fancy slices over there. And there is a list. So we took this work from the work of mathematicians. There's first by
It's Malkin, Ostrich, and Vibornov.
Malkin and not Vibornov, yes.
Ostrich, Vibornov.
But before them, I'm referring to
The one you were looking for is Stembridge.
Stembridge.
Ah, okay.
Stembridge.
Mm-hmm.
And so Craig, I would recommend reading both of them. Very nice pieces. In the case of Stembridge, it's root systems, beautiful piece, and in the case of Malkin and Vibornov, it's about the slices in the Afan-Grassmannian, and they rely on this work of Stembridge.
Mm-hmm. And so just to check, I kind of understand. So things like AG2 and CG2, these things can be like non-normal singularities, or
they are all normal, very nicely behaved.
Oh, they're also nicely behaved and normal. Okay, I see.
Minimal slices, two phases. They satisfy all of the criteria. The AG2, I believe both of them have an SU2 symmetry.
Mm-hmm.
But it's written in the paper, and so I think we wrote down the isolate generating function, so they satisfy all of the criteria I talked about. Those are very nice, simple slices.
I see. And is there, I'm kind of monopolizing a bit, but is there like say a 6-dimensional theory for which this is the Hasse diagram? You write magnetic quiver, so I'm wondering if it's the magnetic quiver for some 6D creature.
It might. My bet would be, so I don't have a good answer at this point, but if it is, my bet would be on the high minus curves. -3, -4. It could show up over there. Now maybe the others have other comments.
So it's not exactly that diagram, but these slices, this AG2 and CG2, they do appear in at least in 4D SCFTs. In the Higgs branch of certain 4D SCFTs, they appear.
I see. Okay.
At rank 2. So if you look at the list that was compiled by Mario, these slices appear.
I see.
And what are the magnetic quivers?
So the magnetic quivers, well, they are given in our paper with Mario and Gabi and Julius for the rank 2. And well, I don't remember now by heart, but they are given all in that paper. So we could have a look later if you want.
Mm-hmm.
Okay, great. Thank you.
Okay, do we have more questions? If no questions now, I'd say let's thank Ami again.
Thank you.
And stop the recording.